Today we will discuss about the image formation by a lens. And first of all, we will discuss about some process by which we can form an image in our through our lens. So this is here principle or construction raised for ray diagrams. So in this case, we have to remember to form an image by a convex or concave lens. There are some definite rules which you have to obey, and this is here the size, image, nature of an image formed by of an object by a lens can be determined by drawing ray diagram. And in this case, you have to consider at least two rays, and these two rays, when you consider these two rays and you obtain an image, and then you can understand the characteristics of those images. For example, let us here discuss about the three kind of rays you have to consider. Number one is a ray when passes through the optical center of a lens. Here is the lens, and you know this is the convex lens and this is the concave lens. And you know that in convex lens, the parallel rays will diverge to a point which is called the principal focus. And you know that there are two principal focus. This is one principal focus and this is another principal focus, and this is called principal focus number two and this is principal focus number one. You know that the distance of these two foci from the optical center are equal, and in the similar way, this is a concave lens in which this is the principal focus number two and this is principal focus number one. And in case of a lens, it may be convex lens or concave lens. If a ray of light passes through the optical center, then it will be undeviated. That means it will not deviate in any direction and it will pass straight away. And here is also in case of concave lens, here is a ray which is passing through the optical center and it will go straight away and it will not deviate in any direction. So this is the first convention of drawing of ray of light which is passing through a lens. So you have to remember for the first case, that is, if a ray of light passes through the optical center, then it will pass straight away without any deviation. And here is number two, another sign convention or another ray convention, which is that if you consider a parallel ray and the ray is parallel to the principal axis. What is the principal axis? You know that this is the principal focus one and this is the principal focus two. And if you join these two focus by two foci or these 2 points by straight line which is passing through the optical center is called the principal axis. So the ray of light which is parallel to the principal axis is always passing through the principal focus point f2. So here is the parallel ray which and it is parallel to the principal focus principal axis, that is f1 f2, and it will after being refraction through this lens, it will pass through the point f2. And if in the similar way, if you take another ray of light in this direction which is parallel to this principal axis, then it will pass through the point f2 after being refracted by the lens. This is the convex lens. And if you take the concave lens, then you will see that if a parallel ray falls on the lens, and this is the principal axis and this ray is parallel to this principal axis, then it will diverge, and it will seem that this diverging ray will come from the principal focus at 2. So in the similar way, if you take another ray in this direction, which is parallel to the principal axis, then it will diverge in this direction, and you will see that it will seem that this ray is coming from this point f1, which is the first principal focus point. So this is the second convention, the ray convention. First one is when you take a ray of light which is passing through the optical center, then pass it will pass undeviated, it will pass undeviated, and it will not bend in any direction. And in the second case, if you consider a parallel ray which is parallel to the principal axis, then it will pass through the uh, principal focus point, or second principal focus point, according to this sign convention. So number 3 is another, here is number 3, a ray of light passing through the first focus f1, as in case of convex lens, or directed towards the first focus f1 in case of concave lens, emerges parallel to the principal axis. That means here is the principal focus point 1, and this is a convex lens. And if you consider that a ray of light is passing through the principal focus point f1, here is the f1, and it will fall on the convex lens at this point. And after being refraction, this ray of light will pass in such a way that it will parallel to the principal axis. So if any ray of light is passing through the principal axis, then it will refracted parallel to the principal axis, obviously in case of convex lens. But in case of concave lens, you see here that this ray of light, it is being seemed that at this point this light is passing towards the principal focus f2. Then after being refraction by the concave lens, it will pass parallel to the principal axis. So this is shown here. So out of these three cases, only you have to consider the first two cases to understand the nature of image is formed by a convex lens or a concave lens. So here is written, discussed, that is discussed here from a point of the object. Although an infinite number of rays travel in all possible directions, but we choose only two convenient rays out of the above mentioned three rays from that point on the object. The point where the rays meet or appear to meet after refraction from the lens is the image of the point of the object. The image is obtained in a similar manner for each point of the object, and all these images points together then form the full image of the object. So to form an image by a convex lens or a concave lens, you have to consider these two cases. That is, one ray you have to consider one ray is passing through the optical center and another ray is coming towards the lens parallel to the principal axis. And if you consider only these two rays, then you can understand the nature of the image, and a ray can fall on the lens in all possible directions and all possible points. So you need not to consider all the points, only you need to consider these two cases, and using these two cases, considering these two cases, you can understand the nature of the image. So only we consider these two cases, that is, one for case number one, the light passing through the light passes through the optical center, and another is passes parallel to the principal axis. So these two cases is sufficient. Now we will learn here that two images can be formed by a lens, and these two images, that means the image formed by a lens is classified into two types. Number one is real and number two is virtual. So first of all, what is a real image? Real image is nothing but the image formed by convex lens. That is, you know that convex lens is nothing but a converging lens. So if you consider a convex lens, and if you consider parallel rays, then these parallel rays will meet at the focus point f2. So here these rays, parallel rays, are converging. So in case of convex lens, actually all the rays will meet at a certain point, and then there will form an image in such a way that that image can be produced, or that image can be seen on a obtained on a screen. So this type of image is called the real image. So real image formed by real image is nothing but an image formed by a convex lens, and in which the rays coming from the object actually meet on a certain point. And in this case, the image obtained in this case can be obtained on a screen or can be found on a screen. So in the second case, the virtual image. What is a virtual image? Virtual image is nothing but the image formed by. You should remember that in case of convex lens, a convex lens actually form real images, but in only in certain case. In a certain case, the real image form an virtual. Yeah, the convex lens form a from a virtual image. So in all cases, convex lens forms real images, but only a certain case it will form virtual image, which we will discuss in later section. So now virtual image actually it is generally formed by concave lens, in case of which the parallel rays after refraction will seem that it is coming from they are coming from a certain point, that is the principal focus number 2, and in that case it is seemed that the parallel rays are are diverging, and from which point these rays are diverging, it is said that an image is formed at that point, that is Z2. So these are the parallel rays, and these will diverge in this direction, and if you put your eye in this direction here, you will see that these rays are coming out from this point, and here actually the image is formed, and in this image is called the virtual image, and this image cannot be obtained on a screen. Okay, so if the rays from a point object after refraction through the lens do not actually meet a point, actually these do not meet a point, but they appear or they seem that they are coming or diverge from a point, that is from this point, and then the image is called virtual. If a screen is placed at this point, you cannot obtain the image on the screen. However, this point is interesting. That is, however, the eye kept between the diverging rays. That is, here, if you put your eye here, you will able to see the image, because the eye lens being convex, and converges the diverging rays from the image on the retina of your eye. If you put your eye here, you can see this virtual image, because our eye has convex lens, and this convex lens will produce real image. This produce real image on our retina. So in this case, you can understand, or you can see this virtual image. So the virtual image is and obviously you remember here the virtual image is erect, that is upright with respect to the object, and in case of real image, it is not, it is inverted. Actually, it is inverted with respect to the object. So here, go to the next slide. This is here the difference between what we have discussed already. From that we can understand the difference between distinction between the real and virtual image. So first one is real image is formed actual due to actual intersection of the rays refracted by the lens. You know it, you understand better it, you understand this. And in case of virtual image, actually the rays do not meet at a point, and they seem or they appear that after a refraction from a lens, it is seen that they are coming out from a point. So in the case of virtual image, the rays actually do not meet, but appear they appear, but it is seen that they are diverging from a point. Okay, so in real image, real image can be obtained on a screen, but a virtual image cannot be obtained on a screen. Real image is inverted with respect to the object, but in case of virtual image, it is upright or it is not inverted with respect to the virtual image. Example: the image of a distant object formed by a convex lens. If you put an object at a distant place, then you will the image that will produced by a convex lens is nothing but a real image. And in case of the image of an object, here is the example of virtual image, that is the image of an object formed by a concave lens. If you consider that an object is placed at a distant place, and you have used a concave lens, then the image that will form is nothing but a virtual image. Now, construction of ray diagram for a lens. So as we discussed earlier, you have to remember the first two first two ray diagrams. Here are also here that these two ray convention once again discussed in this section. So first we have to draw the line PQ, this PQ across the paper, name it is as principal axis. Principal axis. After that, choose a point O on the principal axis, which is called the optical center, which will be called or which will be denoted as the optical center. Here is this. So first you draw a line that is PQ on the paper, and this will be termed as the principal axis. On this principal axis, you you draw a point or consider a point O, which will be termed as the optical center. After that, using O as the optical center, you draw the lens. This is the lens, the principal section of a lens, that is here. So this is the principal axis, and O is the optical center of this lens. This is for convex lens, and you will always use convex lens, because in case of convex lens, the formation of image is very easier with respect to the concave lens. So try to use or try to use convex lens for the image formations. So number two is here you write 2 points f1 and f2, which are equal distances from the optical center, and these 2 points are called this is the first principal focus and this is the second principal focus. And remember that this distance OF1 and OF2 are equal. Okay, so first you have to draw a line on the paper, and this is write it as PQ, and this is the principal focus. After that, you choose a point on the line O, which is and you consider this as the optical center of the lens, and taking O as the optical center, you draw the principal focus, principal section of a lens. This is here. Now, to another 2 points f1 and f2 should be taken on the principal axis, such that this distance, that is OF1, and this distance, that is OF2, are equal. And these 2 points of f1 and f2 are called the first principal focus and single principal focus respectively. So now the third case is if you consider that AB is an object which is placed at a far distance, at a certain distance from the lens. So this is the object AB. So now draw the straight AB here, AB, straight line AB on the principal axis. This is the principal axis to represent the virtual linear object. and the height is actually AB here. So you can choose height as you wish. So you have to draw the object and here by AB, okay, on the principal axis. Now, as we discussed earlier, that you have to consider two cases. Number one is, here is, see, this is all things are drawn once again here. First PQ, this is the principal axis, then the lens with optical center O, after that the object AB here. So now and draw a line which is passing through the optical center. You know that the line or the ray passing through the optical center will proceed without any deviation. So this will pass undeviated straight way in this direction. Okay, this is the first case. And then here is also summarized all these things that we have done in the previous cases. So all things. So this is the lens, this is the principal focus, principal axis, this is the first focus point, this is the second principal focus point. So this is the ray which is passing through optical center and it will move without any deviation. After that, another ray which is parallel to the principal axis, that is this is the principal axis and this is the parallel ray, that is AD. And when falls on the lens, then you know that this ray after refraction will pass through the principal axis Z2, and this is so it will move in this direction, and this ray AOA and this ray DA will meet at the point A. And so if you connect these 2 points or draw a normal on the principal axis, that is in this direction, yeah, this will give the image of the object. So in this, so therefore here actually if you draw this normal at this point, and at this point that will give you the image of the object. And you know that this tip or vertex or tip of this point will form here, and this B point will form here. So in this case the image will be inverted with respect to the object. Now another case is here. If you consider that so just opposite of these cases, here just first ray which is passing through the optical center, this is passes in this direction, and another ray which is taken in this in the form through the first principal focus. Sorry, yes, this is first principal focus. You know that the ray which is passing through the first principal focus will be parallel to the principal axis. So after refraction, this will be parallel to the principal axis. So this ray and this ray after being refraction, so it will move in this direction, will meet at the point A prime or A dashed. So this the point A prime A will be formed. The image of the point A will form at A prime. Similarly, the image of the point B will form here. So just connect this here, you will obtain the image of AB. Obviously it is inverted in this case. So next go to the third one, that is here, so from here we can understand, here it is summarized once again, that this is the see here, this is the object, and one ray is passing through the optical center and it will go here, pass in this direction. Another ray which is passing passing parallel to the principal axis, and after being refraction through the convex lens, it will pass through the second principal focus point and it will move in this direction. And another ray which is passing, you can consider another ray which is passing through the first principal focus, and after refraction through the lens, it will be parallel to the principal axis, and all these 3 refracted rays will meet at the point A. So the A prime actually A prime. So the image of the point A is formed here. And similarly, if you draw normal on the principal axis, the image of the point B will also form in here. So actually a prime b prime, that means, or b prime a prime is the image of the object AB, and it is obviously inverted. So measure the height a prime b prime and the distance o b prime, that is from here o and b prime is here, of the image, and then convert it on the chosen scale to get the actual height or size of the image and position of the image. Okay, you can do this way. Now the same procedure is adopted in case of adopted the ray diagram for a concave lens. In concave lens, the focus f1 is on the right. Here is the f1 is the right of the optical center row, and the focus f2 is in the on the left, in figure, this in this figure the ray diagram for concave lens is shown here. So this is, here is your object, and this is the concave lens, this is the optical center. So first consider this ray A, and in this direction this is passing through the optical center, and it will move straight away without any deviation. So one ray that is in this direction, see here, in this direction passing through the optical center will proceed in this direction. So in this case no deviation will occur, because this ray is passing through the optical center. Now the second one is, so here this is the parallel ray with respect to the principal axis. So this is AD is the parallel ray, and you know that parallel ray when falls on concave lens, it will diverge. So it will diverge in this direction, and if you extend this ray in the backward direction, then it will come from the second focus f2. So the parallel is this AD will seem that it is diverging from the point f2. So in this direction it will seem that it is proceeding in this direction. Now another point, that is another ray that is here. So if this lens would not be here, then this ray will fall on this here in this point f1, that is the first principal focus f1, and this ray will, and this ray when that means a ray which is converging to the principal focus number 1, when falls on the concave lens, then after being refraction it will pass in a direction which is parallel to the principal axis. So this line, see here, this ray, that is the converging ray, this will move in this direction after being refraction. So just extrapolate this in the backward direction, so it will come here. So all the rays, this ray and this diverging ray and this ray, and this is also diverging ray, will meet at the point this here. So this is a prime. So the image of the point A is formed here, A prime. And similarly the image of the point B will form here, B prime. So A prime B prime is the image of the object AB. And see here, notice here, interestingly notice here that this is upright, that is it is not inverted with respect to this. Obviously the size of this image is smaller than that of the object. So what you learn in this, in the two cases, when you use convex lens, then you obtained a real image, but it is inverted, and you will see that the size of this image will higher than that of the object. And in case of concave lens, you see from here that the image produced is upright, that is, it is not inverted, and obviously size of this image is smaller than that of the object. Now come to the another topic, that is characteristics and location of images for a convex lens. So in this case you have to consider the following few cases. Here we will discuss here. So now we shall consider the ray diagram for formation of images by a convex lens which has a focal length of f for different position of the object. and let u denotes the distance of object from the lens. So if you consider, if you u is the object distance and it is called object distance. So now we will consider different cases of formation of images by a convex lens, and in that case you just consider the focal length of the convex lens is f, and the distance of the object from the optical center of the lens is u, that is called the object distance. Now first one is case 1, when the object is at infinity, that is u is equal to infinity. For an example, if you consider that the rays coming out from the sun to a lens which you have, so in that case the object is at a distance of infinity. So in that case, rays coming out from an infinite distance is parallel to the principal axis of the lens. So here is the lens, this is the convex lens, and O is the optical center, and you consider that the object is a distant place, is at a far distant place. That is, you can consider in this case as for example sun. So the rays coming out from the object which is at a distant place or infinite distance are parallel to the principal axis. So here is a ray which is parallel to the principal axis, and here is another ray which is also parallel to the principal axis, and another ray which can go through the principal axis. All of them, this is, since it is this ray will passing through the optical center, and it will go straight away without any deviation, and this ray parallel to the principal axis, so it will meet at the focal point, and this is also parallel, so these will also meet at the focal point. So all these three rays will meet at the point f2. So in this case the image will form at the point f2. So this is nothing but point image. So if an object is placed at a very with large distance, that is infinite distance, in that case the image will form is nothing but a point image. So if you use a convex lens, that is usually you use magnifying glasses, and if you use a magnifying glass, you try to form an image of the sun, then it will give you a point image. Okay, in that case, so for an object which is at infinite distance will give you a point image formed by a convex lens. Now come to the another point that is here. This is also, this is another uh, example is here, and see here in this case what happens. In this case, this is the lens, and you know that this is the principal focus f1, and this is the principal focus, another principal focus f2, and just you look, consider that this, so for this OF1 is the first, this is the focal length, that is you use it as f, here f, see here f, focal length f. So OF1 is f, obviously OF2 will also be f, and just now you will consider that this ray from a distant place object, one ray is coming out in this direction, and that will pass through the object, optical center of the lens, and then it will pass in this direction, and another ray which is parallel to this, so and that is, and consider that that will pass through the principal focus f1, and it will fall on the lens here. After refraction it will pass in this direction, so these 2 points, these two lines will, these two rays will meet at the point a prime. So here a prime b prime will be the object of image of the object which is placed far distance. So it is discussed here just to go through some lines. Now characteristics and location of the image formed. Now you have to understand, we have to study the characteristics and location of image formed. The image at the focus or in the focal plane on the other side of the lens, it is number one is real, number two is inverted, and number three highly diminished. That means you here you obtained here. In this case, you obtained here the image is there, and you put the object in the left hand side, and the image is produced on the right side, and this you see from this figure that this is it is inverted. Obviously it is real because these rays after refraction and these rays after refraction will meet at the point a prime, so it is the real image but inverted and highly diminished. So the brightness of this image will be very poor, very lower with respect to the image a object. Applications, there are some applications in this manner. A convex lens is used either a burning glass or a camera lens. Okay, so if you use a convex lens and falls the sunlight, and you uh, try to use in this lens in such a way that sunlight falls on the lens, and then since it is a converging lens, so sunlight rays from coming out from the sun are parallel rays, and they will meet at a certain point, that is the focal point. And at that point, if you put any burning materials, then you will see that there will be the burning material will burn. So another applications is that the convex lens can be used in the formation of camera that we will frequently use in our daily or practical purposes. Next, go to the third one. Next one, here is the next one. So uh, another some line, focus on a piece of kept on the plane of the lens due to sufficient heat of sun rays. So if you use the convex lens in the sunlight, so what happens then? Due to sufficient heat of sun rays, the paper burns. In a camera, the object lies very far from the lens, and the image is formed at the camera film, which is placed at the second focus of the lens in the second focal plane of the lens. So now come to another case, that is here when the object is bound 2f1, that is u is greater than 2f. You see here that this is the lens, and this is the optical center, and this is the first principal focus, and this is the second principal focus. You know that this distance OF2 is the focal length, that is f, and OF similarly OF2, this is OF1 and this is OF2, both are equal, and these distances are called the principal focal length. So OF1 is f small f, that is this f focal length, and this distance is also f, and you just take another point here which is the distance twice of that of f1, that is this is the 2f1, that is OF2, this distance is 2f, twice into the focal length. Similarly here is also, this point is also 2f2 here, so you have to place the object at a distance far away or distance higher than that of 2f, that is this 2f. So here is the object AB is placed here in front of a convex lens. So you know what you have to do. You have to do first, you take a ray, consider a ray which is passing through the optical center, so it will pass in this direction without any deviation. And number two is another ray which is parallel to the principal axis, that is this is the principal axis, so this is parallel to this, and I know that this parallel ray after being refracted by the lens will pass through the second principal focus point, so through this point, and this refracted ray will pass in this direction. So this refracted ray and this refracted ray will meet at the point A. So the image of the point A is formed here at A prime. Similarly, the image of the point B will form B prime. So just connect A prime B prime, so you will have the image of this, that is the object AB. So and I hope that you understand how this image is formed. So in this case, so first you have to consider that at what distance the object is to be placed. Here is written, here is given the condition that the object is should be placed at a distance which is greater than 2f, that is the twice of the focal length. So measure this. This is f1 focal length, f1, and this is another this is f focal length. F capital F1 is nothing but the focal length f. So use another distance which is equal to this. So that is here. So this distance O into O, this distance, the distance of this point from this point is twice f. So the distance, this point is greater than, at a distance which is greater than 2f, that is the condition is obeyed here. So you place here the object AB. So then, as we discussed earlier, that only two cases we have to consider. Number one is when a ray of light passing through the optical center, it will move without being any deviation, and another ray which is passing parallel to the principal axis after diffraction will pass through the principal focus f2, and this refracted ray and this refracted ray will meet at the point A prime. So A prime is the image of the point A. Similarly, B prime will be the image of the point B. Now just join these 2 points, A prime B prime. So A prime B prime will give you the, or better it is say that B prime A prime will give you the object, a image of the object BA. So from here you can easily understand that this image is inverted with respect to the object. So this is one characteristics of this image. Number one is it is inverted, so that is here, and it is real because these two refracted rays meet here, and you can obtain this image on a screen. And number two, it is diminished. That means the brightness of this image is fewer, very small, very fewer with respect to this image. So the characteristics so therefore if you place an object at a distance greater than twice of the focal length of a lens, the image that will produced by the lens, convex lens obviously, is real, inverted and diminished. Applications: a convex lens is used in this manner as camera lens when object not very far is to be photographed. So you know that in case when you use camera and in that case the focal length of camera is not very large, and in that case if an object which is placed far distance but not infinite, so and this distance obviously is higher than that twice of the focal length, then you can photograph of any object. Number three, come here, number three, when u is equal to 2f, that means the object is placed at a distance that is twice of the focal length. So come here, this is the case here, this is the lens, and you know that this point is the focal optical center, and this is f1 the first principal focus, and this is f2 the second principal focus, and you know that this distance is the focal length, that is f. You take another point here which is twice that of OF1, that is this distance O and this point, the distance of this point, that is say it is B point from the point O is 2f, and you placed here an object AB. So the object placed in this case is at a distance which is just twice of the focal length. So that is there. So not very difficult, it is not very difficult to understand the nature of the image in this case, because we have to consider a ray which is passing through the optical center, and this will go in this direction, and another ray which is parallel to the principal axis, that is, it will proceed in this way, and after refraction it will pass through the optical center, pass through the second focal length f2, focal point, sorry, second focal point f2, and it will pass in this direction, and this refracted ray and this refracted ray will meet at the point a prime. Similarly, that means the image of the point A will form at the point A prime. Similarly, the image of the point B will form here, B prime. So B prime, A prime is the image of the object AB. So in this case, what happens? In this case, that is in case when the object is placed at a distance that is equal to twice f, that is equal to here that is equal to just twice of the focal length f. In that case, the image is obviously real here, because these two refracted rays meet here, and it can be obtained on a screen. Number two is, it is inverted. Yes, it is inverted. You can easily understand that it is inverted, because this point is here, and the point of the image of the point A is formed here. So it is in this direction, upright, it is in this direction, but the image is in this direction, so it is inverted. No problem to understand it. And the size, that is this size, you can if you measure, you can understand. If you draw in your on your paper, on your notebook, you will see that this height and this height are equal. So in this case, the object size and the image size will be the same. So application in this manner, convex lens uh, can be used in terrestrial telescope for erecting, and uh, so in this in the telescope, in those telescope which is used in to view the space, that is terrestrial telescope, you can use this case, use this the formation of image that is happened in this case. So now come to the next one, when the object is between f1 and it should be f2. That is when the object is placed in a distance which is in between f and 2f. That means the distance of the object will be greater than the focal length, but smaller than twice of the focal length. That is here. Here is the lens, where is the optical center, and here is the first principal focus, this is the second principal focus. This distance is f, that is focal length, and another point it is here, that is, and it is 2f1. That means this distance from the optical center is twice that of this f1. So from the point O to this point it is 2f. So our image is placed here, which is greater than f but less than 2f. So it is done here. And now similarly, one ray will pass through the optical center in this direction, and another ray is parallel to the principal axis, and it will pass through the second principal focus and move in this direction. So these two rays will meet at the point A prime. So the image of A is A prime, and similar way the image of V will be here B prime. Just join this line. So in this case, you can easily understand that the size of the image, here is the image, size of the image is higher than that of the object. So in this case, what happens? Obviously it is inverted. Yes, it is real image. Yes, it can be obtained on a screen. And number three is, it is magnified. What is the magnification? Magnification means nothing but magnification is the ratio of the image height to the object height. Since in this case image height is higher with respect to the object height, so if you divide the image height by the object height, it will give you a number which is greater than 1. So in this case object is the object is smaller compared to that of the image. So if once the image size is higher than that of the object size, then it should be called that in this case magnification happens. So the image in this case is magnified. Obviously it should be diminished, that is the brightness of this image will be smaller compared to that of the object. So in this manner convex lens uh, can be used in cinema or slide projects, etc. Okay, you just see these lines. Next point, next go to the next one. Here is the next one. Here is the next one. So number when the object is at f1, that is at the focal point, f1. So this is the case. Here is the lens with the optical center, and you know this is the second focal point and this is the first focal point, and this distance is f1. So in this case the object is should be placed at the point f1, that is at a distance which is equal to the focal length f. So that is done here. Here is the object AB, and you know that as we did in our previous cases, that one ray should pass through the optical center and it will proceed in this way, because in this case this refracted ray will be undeviated, and another ray which is parallel to the principal axis, that is here, after refraction it will pass through which point? It will pass through the second focal point, and after refraction it will pass through this and proceed in this direction. And these two rays, see here, these two rays are parallel to each other. That means they will meet at infinity. So in this case, interestingly, you should note that in this case, if it meet at infinity, that is very very long distances, in that case the image distance will be here, in this image will be here, here in such a way, or the distance is more higher, that is infinite, then the image size will be infinity. So in that case the size of the image will be infinity and magnification will be infinity also. So the characteristics of the image in this case, it is number one is real. Obviously they will meet at infinity, so it is real, and obviously it is inverted and highly magnified. That means in this case the image size will be very very high compared with the image size. Application: in this manner, a convex lens is used in the collimator of a spectrometer to obtain a parallel beam of height by placing the source of light at the focus of the convex lens. Because you don't know what is a collimator or spectrometer, you will understand in your higher classes. So just remember that in this way these characteristics or this methodology can be used in case of collimator or spectrometer. Okay, and what is the spectrometer, collimator, the functions, their characteristics we will know in our higher classes. Just to remember it, that it is used in these two cases. Okay, number 6, here is the another case, in which case the object is placed in between the lens and the focus. So this is the case. In this case you see here, this is the lens, and you know this is O is the optical center, f2 is the second focal point, f1 is the first focal point, and you know that this distance O to f1 or O to f2 is the focal length, that is small f. So this OF1, this distance is small f, and you have to place the object in a distance which is smaller than that of the focal length. So consider that we placed here the object is placed here. So this OF1 is small f, that is focal length. So the object distance, that is OB, in this case is obviously smaller than that of the focal length. Okay, no problem is there. So this is the object, and you know that one ray will pass through the optical center, coming out from the point A will pass through the optical center, and it will proceed in this direction. No deviation will be uh, here in this case. Another way which is parallel to the principal focus, this is the principal axis that is here, and after refraction this will pass through this ray will pass through the optical focal point F2 and pass in this direction, and these two rays will never meet to each other. But if you extend them in the backward direction, they will meet at the point A prime. So actually, if you keep your eye here, you will see that these two rays will coming out from the point A prime. So the here an image will be formed, and the image is nothing but virtual image, because in this case it is appearing that these rays is coming out from this point, that is diverging, not converging in this case. So A prime is the virtual image of A. And in the similar way, the image of B will form here B prime. So just connect A prime B prime, join. So then this P prime A prime will be the image of BA. So from here you can understand that this is highly magnified. This is magnified. This is the size of the image is very high with respect to that of the is not, it is high, or the high or height of the or size of the image is higher than that of the object, and it is virtual image. It cannot be obtained on a screen. Okay, so here is the characteristics. Number one, it is virtual. It is erect or upright. Obviously it is erect or upright, not inverted in this case, and it is magnified. Obviously it is magnified. It has applications, important applications. These are: a convex lens is used as regular lens, that is a magnifying glass or a simple microscope, to form a magnified virtual images of a teeny object. To understand, if you wish to examine a very teeny object, then you have to place this teeny object in between in a distance which is less than that of the focal length, that is in between the optical center and the first focal point. Then you will able to see a magnified image of the teeny object. Obviously it is virtual, it will be virtual. So now come to some inferences. From the above, we notice that both the real as well as virtual images can be formed by convex lens, and you know that only one case, only this is the single case, only one case in which convex lens forms virtual image. So you have to remember this, in which case a convex lens forms virtual image. When, so the case is, or the condition is, when the object is placed in between the optical center and the focal point. Okay, or it is better to say that when the distance of the object from the optical center is smaller than the focal length. In that case the convex lens will form a virtual image, and this virtual image is, the magnification of this virtual image is high, obviously large. That is, the size of the image is higher than that of the object. So that is there. To the size of image, magnified, diminished or same, also depend on the position of the object. When object is very far up from the convex lens, a real, inverted and diminished image will be formed at the focus. This is the first case. When see here, this is the lens, and when the object is very large distance, then you know that you already seen that you have already seen that the image will be formed on the focal point here, formed here. So that is written here. Very far off from the convex lens, a real inverted and diminished image is formed at this focus. As the object moves towards the lens up to 2f, the image on other side of the lens moves away from the focus of the lens to 2f. However, the image found will remain real, obviously real, inverted and diminished, obviously, but its size will gradually increase. Okay, and you can understand this in your previous set that we already discussed these cases. So now go to the next one. Here is the next one. Here is the next one. So next one is an object. As object comes to the position 2f, the image is real, obviously real, inverted, yes, and same size. It is obtained already. It is obtained at the point 2f on the other side of the lens. Okay, it is also true. We already found it. And on further moving the object from 2f towards the focus f, the image will remain real, obviously real and inverted, but it becomes magnified and is formed away from 2f on the other side of the lens. Okay, when object comes at focus f, the image moves to infinity. Okay, you know here, you know all these things. And finally, on the on further moving the object from f towards the lens, that is the object is pod between the optical center and the focus, then then the image will be erect, upright, and magnified but virtual. Note, the above observation can be same if the lens is moved away from the object. Okay, if you placed object here and the lens is, if you move the lens away from the object, then all these things will happen in the similar manner. Here is a table in which important information is given. Number one is here is position of the object, position of the image, size of the image, nature of image, and applications. Just you will go through this. All these things we have already discussed. So I am skipping this table. So now characteristics and location of images for a concave lens. Now come to where number one, when the object is at infinity. So here is a concave lens, and if you consider that the object is at infinity, then all rays will be parallel to the principal axis that is there. And you know that this is the second principal focal point and this is the first principal focal point. So this is parallel rays, and this ray will pass through the optical center and go in this direction. Okay, no problem with this. And this is parallel ray and this is also parallel ray, and you know that when parallel rays falls on concave lens, they will diverge. So these will diverge in this direction and this ray will diverge in this direction. But if you proceed this in the backward direction, extend in the backward direction, they will come from the focal point f2. So when an object is placed at infinite distance, its its image will be formed at the focal point, and it is point of image. Okay, it is point image, and obviously since it is diverging from this point, so it is virtual image. So characteristics of this image is what? It is point image, it is virtual. Okay, it is virtual and point image. Now another thing is here, if you consider that here is your concave lens and these are parallel rays. Okay, no problem is with here. And if you consider that this is a ray which is passing through the optical center, then it will pass in this direction, and this is another ray that is parallel to this ray. Okay, no problem is there. So it will fall on this, and after that since it is converging, because you see here it will seem that it is, if this lens would be not there, then this ray will meet at the point F1. So this is the actually this is converging ray, and this converging ray uh, after refraction will come parallel, or will go through to a direction which is parallel to the principal axis. So remember when for a concave lens, if parallel rays parallel rays fall on it, then it will diverge. Okay, this is diverge from the second focal point. And if another ray you would consider which is converging towards the first principal point, then uh, after refraction they will move in a direction which is parallel to the principal focus. So this is converging to F1, this PQ, this ray, and this will be these will move in this direction after refraction. So if you extraplot these in the backward direction, then this ray and this ray will meet here. So here you will obtain a prime b prime of the object image, and this image is upright obviously, and obviously it is virtual. So it is virtual and upright. Okay, so next go to the next one. Here is next one. So all things are written here what I have discussed previously. Now characteristics and location of the image. So number one, the image is at the second focal point f2. Okay, and it is virtual, obviously erect, obviously, and highly diminished. And you understand, or you have to remember that in all cases the brightness of the image will be diminished with respect to the object. Now applications, a concave lens is used in several cases, and it is written here. Just look at it, just read it. Now go to different cases that we discussed. In the case of convex lens, all these things will be discussed in case of concave lens also. The first one is when the object is at any finite distance from the concave lens. Consider that in this case the object is at a distance which is not infinite, it is finite, which can be measurable from the concave lens. And you see here, this is the optical center, this is your concave lens, this is f2 the second focal point, and this is f1 the first focal point. This distance, that is o f2, this is the focal length, that is f small f, and obviously this OF1, this is also focal length, and you take here another distance here which is just twice of this distance, that is this distance. The distance of this point from the optical center is twice f, and it is similar manner, it is also 2f. Okay, now place here, the object is placed here. So this distance is measurable, and it is not at infinite distance. So now you have to consider two rays, one is passing through the optical center, and you know that these will be undeviated, so it will move in this direction. So this is done here, and another ray which is parallel to the principal axis, that is the principal axis is here, and this ray AQ, this is parallel to this. So since this is parallel ray, you know that this parallel ray will diverge after refraction. So the diverging line is in this direction, and just we extraplot in the backward direction, and you will see that this ray is coming out from f2. Now you see here this line, this ray, and this ray will meet at the point A prime. So the image of the point A is formed here at the point A prime. So similarly B will form here, B prime. So A prime B prime is the image of the object AB. So it is very easily understandable from this, or noticeable from this, that this is this is this image is the size of the image is smaller, so compared to that of the object, so magnification is not happened or occurred in this case. There is no magnification. Number two is the object is erect, obviously erect or upright, that is in this case no inversion is happened. And number three is obviously the image, the brightness of the image will be very smaller compared to that of the object. So characteristics of this image will is summarized here. The object is virtual, erect, and diminished, and no magnification in this case. Application: concave lens is used in spectacles for the short-sighted person in this manner. Okay. Number inference from the above, we notice that irrespective of the position of the object, the image formed by a thin concave or divergent lens is always virtual. Obviously, this is virtual, and upright. Obviously, it is upright and diminished, and it is situated on the see that it is situated on the same side, in the same side as in the case of the object. So you remember, just to recall, that in case of convex lens, in all cases the image formed on the, if you consider that the object is taken the left side of the lens, the image were formed on the right side, but except one case. In that case, in case where in which the object is taken at a distance which is smaller than that of the focal length, that is when the object is taken in between the optical center and the first principal focal point, then the object and image will form in the same side of the lens. But in case of concave lens, see here, the image here is the object and this is the image. Both of them are in the left hand side or the same side of the lens. So that is here written here. Another point is here, when the object moves from a large distance towards the lens. See here, for the first case, the object was at a very far distance. Okay, so and in this case, it is moving towards the lens. So the image shifts towards the focus, towards the optical center of the lens, and the size gradually increase, but it is always remains smaller than the object. So in this case, you see here that when the object was taken as infinite distance, that point object was formed at the point focal point, but in this case that is the object is moving towards the lens. So here you see here the object is also moving towards the optical center, and you also observe that in this case the point, it was point object when the object when the image was point image when the object was at infinite distance, but here the size of the image is increased in this case. Okay, that is here. But when how much you go towards the lens, the size of the image is always smaller than that of the object. Okay, when the object is at a distance equal to the focal length of the lens, the image is exactly at the midpoint between the optical center and the second focus point of the lens. The table is here. In this table all things is summarized. Okay, so next go to the next one. Here is the next one. So this is here. So now sign convention and lens formula. So okay, we will discuss this in our next class. So just you have to go through